So let's see where we get this. We take all the elements and divide them into buckets. How long does that take? That's not included here actually. N by P, right? All processors take just one chunk and keep giving them into the corresponding bucket. How many things go into the bucket?
Not necessarily.
That's not my question. Let me rephrase. When a processor puts something into a bucket, how many different sources are elements coming from into a bucket? P different places, right? You need to put them in the proper place. Where would you put them? You need to figure out how many elements you are going to send to a given bucket. Right? So before you start sending them, you have to do some accounting. So you figure out, I have so many elements in bucket 1, so many in bucket 2, so many in bucket 3, so many in bucket 4. How many things do I generate? B numbers. Because I have B buckets where I am generating some number of elements into. There will be others, or B minus 1 others, who are also generating B numbers. Right? Everybody is generating B numbers. Right? B numbers are the number of elements in the B buckets for a given processor. Each processor is taking its N by P chunk and saying, you go to bucket 1, you go to bucket 2, you go to bucket 10, you go to bucket 14. And so there are P buckets, B buckets. No, we are using P. The number of buckets is equal to the number of processors. So we are generating P numbers, right? Every processor says, for every bucket, how many elements in that bucket. Now we need to figure out where these elements should go. Right? So we need to figure out the sum of prefix sum of bucket 1. Right? And one side effect of that is that we know the sum, the number of elements in bucket 1, because that's what the last processor will have. A prefix sum of bucket 2, prefix sum of bucket 3, and prefix sum of bucket B. Right? Each prefix sum will take log P time, and there are P prefix sums to do. So it's P log P to do those prefix sums. At the end of this, you know where to start putting elements for every bucket for your processor.
So for this to be done, we don't need to do the internal prefix sums within the bucket.
You just need to know the counts, no prefix sum. You just need to know the count.
Count of the whole bucket.
Yes.
And then prefix sum over the bucket level. Yes.
Prefix sum across the buckets, but you still need to know. No. You still need to know prefix sums across the bucket, right? So where do you start writing bucket 1? For that you have to know the sum
before the
of bucket 0.
Before you
of bucket 0. Right? The total number of elements that are going to go in bucket 0,
right,
which was a side effect of the prefix sum.
So why to do this prefix sum?
For bucket 1?
Yeah. When within the bucket, how do we use that internal?
You have to know. So you are generating B numbers, right? B numbers are the number of elements in the B different buckets. Where should you write them? At the end of the day, you have to generate sorted sequence, right? So sorted sequence means bucket 1 followed by bucket 2, all the bucket 1, right? All processors bucket 1 followed by all processors bucket 2 followed by all processors bucket 3, and so on. So to start writing things into bucket 3, I have to know where bucket 3 begins. Bucket 3 begins after bucket 1 and bucket 2 are exhausted, right? And so I have to figure out where that begins, and so that's where I need the prefix sum of bucket 3, so that I as processor number 10 will know where to put my bucket 3 elements. Okay. All right. What other?
You know the log square P in compare and split in.
So, one is we know where to start bucket 3, but inside bucket 3 they are writing parallel, right?
They're writing parallelly.
So they that even the sub range they also need to know for sub range.
Absolutely. That's why they need to do a prefix sum of bucket 3.
So there's two prefix.
There are B prefix sums.
Each bucket, n minus 1 buckets, plus inside that bucket also where they start putting.
So when you do these B prefix sums, you are going to generate the sum of bucket 1 and sum of bucket 2 and the sum of bucket 3, right? Then you do a prefix sum over the sums to figure out where bucket number. So there are local prefix sums which says within my offset, processor number 10 for bucket number 5 goes to this position, processor number 11 goes to that position. But where does bucket 3 begin? That's from the sum of all the buckets. How does bitonic sorting work?
So you take the alternate element.
You
split it, do continuously.
It takes log n time to merge two bitonic sequences into one. Similarly, it takes log n time to split it into top half and right half. Right?
Or one time.
Into left half and right half? No, to sort it. Sorry, my mistake. Not to simply split it into top half and bottom half, but totally sort it.
Log square.
Log square, right? So if you recall, in fact, why don't we go there? This one. The last stage took log n time. Stage before that took log n minus 1 time. Stage before that took log n minus 2 time. And so the total number of phases where you are doing compare exchanges, right? Each column is a compare exchange, and the braces at the bottom give you this different stages. So all the compare exchanges added up across all the stages, meaning all the compare exchange columns added up across all the stages would be log n times log n plus 1 divided by 2, right? Log squared n. So they are log squared n compare exchange sets that are done. Each set is done in parallel because everybody in parallel is comparing, exchanging something. And so now when we come back to this.
That is the one you are asking. You are asking cyclic bitonic to this one here.
This is bitonic sort.
This is cyclic also.
Yes, it works on cyclic also. What is the same?
Well, you asked something in the beginning of the class regarding cyclic.
I asked that I had shown you an example in class of just pure sequence, increasing and decreasing. And I asked you that, of course, it will work for all bitonic sorts, even if it's a cyclic shift of pure increasing and pure decreasing. I asked to go convince yourself, prove to yourself that the same mechanism, the same algorithm works even if you have a shifted bitonic sequence. You can still sort it. Okay, so log squared p comes from that many stages. But now instead of compare exchange, which was done in one time, you're doing compare and split. Okay? So compare and split is compare exchange over some n over p things. So there are log squared p stages, but each stage now is taking n over p time instead of one time. It's n over p log squared p. Okay. Any?
I have some real world system issues. So, for example, in all these sorting algorithms, whatever we are studying, we are assuming that the data is already inside the main method.
Yes, because we're basically thinking PRAM as in the back of our mind all the time.
But that's not always the case, right?
Absolutely.
Because if you have to sort 100 terabyte of data, you'll never have machines which have 100 terabytes of memory.
Well, never say never, but yes.
Yeah. So you'll have to write to disk at some point of time within your like in between your sorting algorithm itself. And if you are like taking, for example, this kind of parallel bucket sort, and like when each machine is receiving from multiple machines, you are not writing on only one particular chunk of data at one point of time. If you are doing it naively, then you may end up writing like doing 20 different writes at the same time, 20 different reads from the disk at the same time, which will basically kill your system.
Yes.
So like, how do you take these?
There is an entire area which is based on disk data structures.
Yeah, but like does this complete area in any ways gets in tune with the PRAM model that we are discussing?
Not exactly. So let me explain what I mean. Even for a single core machine, sequential algorithms, there is an area that is disk IO based algorithm, disk data structures, right? Often also called off-core computation. And just as we have seen that you can't simply take, at least all the time, a sequential algorithm and expect it to perform well in parallel, same thing works. You can't simply take a basic sequential algorithm and expect it to perform well in that disk IO model. And so now we are having the same problem here. You simply can't take a PRAM model and expect it to always perform well in the disk IO model in the PRAM context. That is an area that's not well studied at all. Disk IO model in the parallel context.
But
it's well studied in sequential domains.
Disk IO is like any system at all, to work at all, you have to think about the IO, right? We take this up like in the course.
Actually, there used to be a course called File Systems and Data Processing. It's gone?
I haven't seen in the past.
That's where things like this was discussed. Yeah, you can actually have an entire course on off-core computation or out-of-core computation.
So my point was that because this is this is an absolute necessity for like any kind of parallel computation where you are dealing with large things, shouldn't we discuss it a little in this course? If we have time.
That's the thing. We will not have time. There are other big swaths that we have not touched upon. I would like to go through them because just setting up the model for disk IO, and in fact, as I also earlier said, in the context of parallel algorithms, PRAM model, that area is not well studied at all. So there isn't even enough background material to cover if we are thinking in context of parallel models. So that would make a lot of sense. You can then pull in concepts into parallel domain, but doing that in a sequential context itself is a good topic that should be covered in some course. One course on another. And
right. So back to the same question: how do you sort when you have so much data that you can't fit it in the PRAM, like in the RAM?
So the model,
it's not covered.
You look at out-of-core sorting.
We can perform the two-way merging or multi-way merging.
No, there are merging techniques, but you have still to think. Your cost model changes, right? Instead of asking how many steps of computation you're doing, which you still do, right? Just like you're sometimes saying so much computation and so much communication, you say so much computation and so many blocks of data read. Okay. And there is notion that there is fixed block that you can read. If the block is contiguous, you can read it together. If it's not contiguous, then it becomes a different. So that's the basic idea. But and sometimes algorithms can change significantly to account for to have a low cost on that cost model. All right. Anything else that we need to
compare? Mod-01 sort, in which you have some log factors.
Mod-01 would go later.
This is basically P into 2n by P.
This is not completely obvious looking at it, but it is correct.
It's P into n by P.
Not exactly.
Means the last step
Of course, P n is equal to P into n by P, but
so we have to repeat the step P times, and the last step is taking n by P. So total time would be ordered.
And what about the first one? I think you got it basically right, but I didn't want to give you the answer. Why don't you think about it? It's in fact it's on the slide. If you just do the analysis properly.
Each process eventually is.
Yeah.
The constant operation is same as the one that you find out in contextual pattern.
So at every level you are doing the same amount of work as the previous level divided by 2, which is going to add up. It's like a binary tree. You got n nodes. I did not have the patchers or even merge.
Right, over here, can you explain why you do the quicksort on each block? Or whatever you do? So, you're just doing a parallel splitter selection. Right?
Yes. So the idea is that from each block, you pick out sufficiently distributed set of numbers. Right? So you would like some numbers at the lower end of the block, some numbers in the middle end of the block, some numbers at the higher end of the block. And there are other probabilistic methods that do that. But one way to do that is simply sort that block, quick sort or otherwise, it doesn't matter. It's local sort. That's why it says quick sort, because it's supposed to work well. And then pick every B items. And that's what you are picking from every one of the blocks. So now you've got B squared items. These are sorted, and you need to sort them further. So there are n things, you want to merge n things into one. And because these n things are already B things that you are getting is already sorted, you can do it but in better than B log B time. But for the time being, I think, or rather there are B squared things. So you can do it better than B squared log B time. But because that doesn't add up in the final analysis, we'll just leave it at brute force. And then once you have figured out the splitters, which with a high probability is going to distribute the elements into B relatively uniform buckets, you simply figure out where your element goes, which is prefix sum. After prefix sum, that's where B log B comes from.
So you're having a deterministic guarantee that no bucket will contain more than.
Yes, yes.
That's why you did the initial sort.
That's why this initial sort is necessary. Right? Even if you didn't, there are probabilistic methods where you say you don't initially sort, but you say that no element is more than some B by 2 away from its original position. And then you can come up with another bound on how far that any 2 buckets may be from each other. Okay, and this is what we were looking at. Is this clear how this works? Yeah, so you didn't look at it. This is for single bit only. I've got one bit at zeros or ones, and I want to know for my position or my number, which is a 0 or 1, where should I put it in the output? Okay, it can in fact be done in place. Once everybody knows the number where it needs to go to, they in parallel can write it there. So the first thing negates the bit to do a prefix sum, and basically it's doing a prefix sum on the zeros. Okay, because if you negate the bit, then zeros becomes 1, or zeros become ones, and then you are doing a prefix sum on those ones. E scan is for exclusive scan, right? Something we saw in the OpenMP context, meaning that you are prefix summing everything until you, not counting it, right? Before you. And so P sum is how many zeros are before you, right? And total number of zeros is the p sum of the last guy, but it was number of zeros before that guy. If the last guy is also 0, then you have to add 1 to it. So you add last guy's bit, last guy's not bit, negative of the bit, or negation of the bit. We also need to know how many ones there are, right? At the end of the day, you need to know how many 0 elements there are. If you are a 0 element, then you need to know how many 0 elements are before you. If you are a 1 element, then you need to know how many 1 elements are before you and the total number of 0 elements, right? And so, if you want to figure out how many 1s are before you, you take your index and subtract how many zeros are before you. There are so many elements before you. If your index is 5, there are 5 elements before you, of which you know 3 are zeros, others must be 1s, right? So, index minus p sum is the number of 1s, and to this you are adding the number of zeros, total number of zeros. So, now you are getting your prefix sum for 1s added with the number of zeros. And so, the last step that remains is, if your bit was positive, then you should take the second value, which is number of zeros plus the 1s prefix sum. Otherwise, you should take the first value, which is just the prefix zeros, prefix sum of zeros. Okay.
How do we do this in place? So I can find the indexes in an uppercase array. But how do I write it in?
Once everybody knows what its position is in the output, everybody has computed it. You do a barrier, you figured out that everybody has done it. Now you know where your bit goes. You simply write to that position. Everybody's bit goes to a different place.
But I've copied the record to a different place. And
why? To the same place. Into the same array in a different slot.
But so if you're assuming the PIRA model, then I can say that okay, everything is being read in parallel and everything is being written in parallel. But when you actually try to do this,
you can do this on CUDA this way. You do assuming it's within a block, you do a sync after you have finished all of your operations. Then read the element at no, you've already read your element. So this.
No, that's what I'm saying. So if I'm not read my, so there's a big record that I.
Okay, the rest of the rest of the record. So you read the record, then you sync, then you write it. Everybody has read it locally.
But then you are assuming n processes.
No, I'm just assuming n memory locations, n local memory locations.
But if everyone is doing that, so won't be needing a temporary array to store.
Yes.
For example, if you're
okay, so
OpenNP, then you need a temporary array, then it won't be in place.
All right. So my notion of in place was in place in global memory, and that's why I was referring to CUDA. You read it in your register. So assuming that it's a limited size record, you read it in a temporary space and you write it.
No, but you're using all the n extra space.
You are.
We won't call that in place.
That's a tough one, I would say. In sequential context, it would certainly not be called in place. In parallel context, every time you're reading things in parallel and writing things in parallel, you have to have space for reading n things, right? And so you're not really making a copy of n thing. You're simply whenever you in a PRAM step, what do you say? You read an element, do local computation, write an element. So when you read an element and write an element in the same place, is it in place or not? When you are using n registers because you have n processors, is it in place or not? Technically it's not, but in the parallel context you'll probably call it in place because you're not really making in the shared memory an additional second copy which needs to be accessed by multiple people. Okay. All right, so there was a quick example which I'm going to rush through. The original number of bits, then their negation, then the prefix sum on the e-scan on the zeros, and the second one is your index, and the last column, last row is effectively the e-scan on the number of ones. Okay, let me stop. Questions on the basic 1-bit sorting? How does this work now when you have many such 1-bits? You can simply repeat it, right? K times if you've got k bits. You may also block it, right? So instead of saying just 1 bit at a time, I can read k bits at a time or k1 bits at a time. How will the phase change if I have k bits instead of just 1 bit? Now I've got k bucket, 2 to the k buckets.
For each
So you do prefix sum for each individually. Either you can do it in one go if you can copy multiple numbers, or you just do it k times. Typically doing it in one go would be much faster.
So how do you do it?
You still have the same binary tree that you construct for prefix sum, right? But at each time, instead of saying take the sum of this and this, you're taking a sum of k things, right? Pairwise sum of 2 arrays rather than 2 elements.
So if we are taking the key as the digits 0 to 9, then we can just compare the digits and then we can divide in 10 buckets. Would we say that we are comparing 32 bits?
No, you would compare, for example, this algorithm by Garland and company, which actually got published in 2009. So they had an earlier version, 2008 also, which divides it into 4 bits at a time. And then it really is taking the entire input in, masking out those 4 bits, or checking those 4 bits, and then doing something with it. Right? So,
is it better to, for example, if I'm given only the numbers, and I'm doing radix on the numbers, so is it better to take 4 bits or just compare the entire numbers, digits?
So one buckets are
meaning that your entire key, the entire digit is your key. How many buckets do you have? No, 1 digit at a time, you mean? Okay.
Or I take only the first 4 bits of the digit and then form.
What do you think? So basically, is that your question? Is it mod 16 or mod 10? Right? Base 10 or base 16? That's your question?
So what I'm saying that, for example, in the Radix Sort, we go from LSB to MSB. So we started LSB, and then one thing is that you have only the digits, right? So you can form 10 buckets, and you can say anything with 0 can go to first bucket, with 1 to second bucket. What I'm saying is, it better to compare 0 and 1, or you compare the first 4 bits of the digit and then divide into
Pairing to 10 buckets.
First 4 bits will tell you whether it's 0 or 9. Is that what you're saying? I'm not sure I fully understand your question.
It's actually the same thing. Right? See, look at the
I'll ask you later.
Okay. But would you like for it to be base 16 or base 10? 16 is easier, right? You can get the 4 bits out. Base 10, you have to do some work to get the digit out.
Then first store in base 10.
Sorry?
you store it in base 10.
Nobody stores it in base 10 except we. Okay, so it does it a block at a time. It brings in a block into the shared memory, and in the shared memory it simply compares your number. If 0 goes to 0 bucket 1, and locally you can do it, kind of local, at least in the context of global memory. You can do it 1 bit at a time. You can simply look at all 4 bits together and make 9 buckets. what would you rather do? Which would you rather do if you're doing it on CUDA? No, multiple of 16 is fine, but one phase of this is 4 bits worth of comparison, right? One way to do the 4 bits worth of comparison is to do 4 stages of 1 bit sort, like you did earlier, or one stage of 4 bit sort, where you say, I will generate 16 different prefix sums. Anyway, and that there are lots of parameters that go into that, so that I don't expect you to be able to come up with that answer quickly. But at least from the point of view of doing this in shared memory, they claim that doing it together is faster than 4 iterations. So that's why this is the 2008 paper, where they first presented the 4 iteration version and then they updated it. Anyway, so now they generate these histograms which can be prefix summed, and you figure out where your digits number 7 go. Okay, and then now you go back to global memory, put it in the right place. You do it one block at a time. What about across blocks?
What for the blocks? You did do this individual for each block.
We did this individual. If we wanted to do it for the entire block, what would have to change in this algorithm so far?
Bucket would need to be kept.
You'll have to know where this bucket begins, right? So there are 16 buckets for you to handle, right? But there are other blocks also handling 16 buckets, the same 16 buckets. So you have to do a prefix sum across all of them. Which means they have to come up with their histograms before you can do that prefix sum. Alternatively, you can simply generate your results locally, and you can say, now I've got these 10 buckets, my 10 buckets are stored at this place, your 10 buckets are stored at some other place. Then later on, you simply move these buckets around. Okay. All right. Enough about Radix Sort, which by the way is conventional wisdom that for integer type sorting, which is where a lot of sorting dollars are devoted, Radix Sort works the best, especially in the parallel domain, and there's been a lot of work on CUDA which all points to the same thing. Okay, let's get back to sorting optimally. Okay. Remember merge sort? We've already discussed it when we were talking about merges, when we started talking about sorting, and we are going to extend it to do fully optimal sorting, which is really fast, meaning it's n log n and can be done in log n time. The basic merge was, not the basic merge, the fast optimal merge was how fast and how much work? Log n fast and n work. Okay. So if you just apply this algorithm, you get optimal sorting, right? N log n work, because there are log n stages of merging, and how much time? Log n log squared n, which is much better than log squared n, which has been kind of common in several of the sorting schemas. The question is, can you do better? And the second question is, and this is where you will also see some examples or some cases where we, instead of thinking just in terms of here is the time and here is the work complexity, we'll actually try to come up with an algorithm where if we know that there are P processors, so we will do the scheduling rather than have the basic the PRAM scheduler that we had talked about earlier. Okay. So let's think about that in the merge case. We have P processors only, n elements to merge. And with the knowledge of the optimal algorithm and all that, what would be a good way to proceed? We might say we'll take 1pth of the total number of elements and we'll do local sorting. Well, hopefully local sorting is significantly faster. At least we know how to do it fast. Than shared sorting. So we'll do local sorting at n over p elements, and then we'll merge them. We will merge them one pair at a time. How will this work? You have n over p elements of the leaves. You merge 2, and you merge 2, you have p by 2 processors needed for this, right? Just at the leaf level. So maybe you can say I start with 2n by p element, 2n elements, and so we'll generate 2n over p leaves, and so we'll with p elements. No, let me restate. 2p leaves. We'll generate 2p leaves so that with p processors we can merge them in parallel. Okay, order n over p each, merging 2 at a time optimally. Log n over p and order n over p work. But that only gives me the previous stage, one level. What about the next level? Now the merge sizes, the element number of elements in each group has become twice. The number of groups has gone down by half. So I would at least now like that 2 processors share the merging of 1. Right? So 2 processors merge the first 2 pair, 2 processors merge the second pair, 2 processors merge the last pair, the p by 2f pair. Next time, 4 processors per merge, and at the end, p processors for the entire merge, right? And so you add it up together. How much time will it take? You can punt on the leaf level. You can say that's a sequential merge, but beyond that, it's a parallel merge. Sorry?
But the limited parallelism.
Limited parallelism, yes. So we are merging certain size blocks with certain number of processors. But always 2 at a time. How long will it take? These steps. Time, total time.
So the number of steps will be, we started with one processor working on one group, and finally we reached all processors, p processors working
on the entire thing, right? But how long does it take for all the processors working on the entire thing? And then similarly, half the processors working on half the thing. I'll let you work this out. It's a variant of this is already in one of the earlier slides, so it shouldn't be too much trouble to refer to it. And this is also very related to the one that I said work out earlier today. The bottom line is that it's not going to be order n log n. But you think all the merges are in order 1? So you'll have to multiply, you have to figure out, it's not just multiplication, it's adding up sum of the number of steps per level. Okay. So now from this 2-way merge, let's move on to n-way merge. Okay. Let's just simply take those n things at the bottom and merge them using p processors. P things at the bottom, merge them using p processors. Okay, and the idea is, I hope I didn't have all the slides for the batchers odd-even merge sort, but I hope you have looked at the slides. I didn't have it when I presented it in class, but it was posted. Sorry? Yeah, it's in the slides. Doesn't matter. If you have not seen it, you will not suffer, because this uses a construction that is very similar to batchers merge. But you can, even if you haven't seen it, think of this as just a fresh algorithm. And if you have seen that connection, then you should be able, if you've seen that algorithm, that you should be able to make that connection. Okay, we are going to begin with an assumption. We'll say n is equal to p squared.
Just one question. So by did we study batchers, then we had a optimal merge, means a better merge. Batcher was auto log n,
Yeah,
and the one we studied was auto log.
because batcher's extension is going to get better than optimal merge, which is what this one is. Okay, and then after this, we'll also go back to the work time complexity mechanism, and in fact, even in that mechanism, you can come up with an n log n work and log n time algorithm. This one is relatively simple. The next one is a bit involved and sometimes non-intuitive. Okay, so we'll start with the assumption that we have the number of elements, which is square of the number of processors we have, and the algorithm is listed one at a time. You divide. We are merging two sorted lists, right? So this is a merging algorithm so far. We have L1 and L2, and we are going to merge L1 and L2 using P processing. L1 is sorted, L2 is sorted. So what it does is it takes every pth element in L1 and every pth element in L2 and generates a new list. How many such lists will it generate? So 0th, p minus 1th, and so on will be one list from L1. Similarly, a similar list, a matching list can be generated for L2. Then the next list will be 1, p, 2p, and a matching list from L2. The third list will be 2, 2p plus 1, 2p plus 3p plus 1, and so on. And so we are generating how many different lists? P lists. Okay. The processor PI simply takes one of these pairs, ith pair, and merges it sequentially locally. And you'll see that's the focus here, to try to do more and more things locally. And it puts it back in the place where so it's not thinking, it's again in place, right? So every I'm processor 0, so my elements are at 0, p minus 1, 2p minus 1, and so on. I think of that as an array. It's just my stride has become bigger. And so I pick up apparently two arrays, and each is individually sorted, and my output is going to be the left half of the combined sorted list, the merged sorted list, going in the left array, and the right half going into the right array. Okay, so in place, I'm going to put back the sorted lists. The surprising thing is that elements aren't too far away from where they should be. Okay, actually, it's actually at most p positions from its the rank value. So how do we bring it back to its final position? The rest of it is not that out of the way. Once you believe, and we'll look at the reasoning for this this part. Once you believe that things are within P of each other, then bringing it into its place shouldn't be too hard. You sort what locally?
The new element just get out.
Okay. But I don't want to sort n over p. You would, at the end of the day, you have to do that, right? Because L1 will be the sorted left half, L2 will be the sorted right half. What I do not want to do is take this entire list and resort it, right? Because that is sorting of half the size that I began with. And that's going to kill my efficiency. So it's actually not that hard. You divide, it's already divided kind of. You still think of it as blocks of P. Then you do the odd even merge of batches. Okay. You take block 0 and 1, merge it. One processor does it. Another processor is in the meantime merging 2 and 3. The third one is merging 4 and 5 and so on. Okay. We're not done yet. The next step, you let alone 0 and you take 1 and 2 and merge it, 3 and 4 and merge it, 5 and 6 and merge it, and at the end you're going to get sorted answer. Why is that? After the first iteration, why is the leftmost block, which is not participating in the second, in step number 5, why is that sorted? Every element that started off in that block was at most P away from its position. So where all might it have gone? At most into the second block, right? And so one of them has sorted those two, right? Merged those two lists and put it in the right place within that much. But we know that it only needs to be within that much. It doesn't need to go beyond it, right? And same way, element that is within P of its position, this way or that, either you sort with your left block or your right block, it's going to get in its position. If you do both, then you guarantee that it's going to get in its position. All right. Why are things only...
Still the blocks would be unsorted, right? Block 1 and block 2 may not be sorted within themselves.
Good question. Actually, they are sorted. We haven't proved that yet.
Or did we begin with? We had 2 sorted lists, right?
We did have 2 sorted lists. No, it's not immediately clear that you're going to get a sorted result. Although you will. You have taken every pth element, right? So P different things are involved in sorting this block, the first block. P different processors. First processor was only looking at this element, second was only looking at this element, the third was only looking at this element. This was sorted when we began. But then somebody is bringing in other things here. Will it still remain sorted? Right? Processor number 6, for example, was taking every pth element starting at 6, and it's going to bring something else. It might bring something else from there, but that something else is smaller than. Sorry.
Consider 4 elements to contribute to an less another, and then we can say that.
You can't say that based on 4 elements, but that may help you figure out why they are sorted. When you take an example, you understand the structure of the problem. It is a little, yeah, you can draw a connection with Python as well.
So the element that we bring in is the smaller than, it can be, it will be smaller than the...
It will have to be smaller.
that was already there, right? But it may not be necessarily.
It may be too small.
It might be too small.
Right?
That's why we are saying that the new list will be having elements at most p away from its file. We are sure that it is not too small, then it is the file.
It can be, right? Let's look at the proofs. It is not its final position because it is not necessarily.
Maybe it may not be necessarily as big as the previous one from the numbers previous to it.
Right.
It may be too small.
Right. It need not be greater than every number before it. Right. So in fact, I have to define what I mean by these things are sorted. These things are sorted or ordered in a certain way.
So I think definitely you can draw diagrams and then explain.
There is a diagram
Diagrams with some values.
which you cannot read, right? Let's see if we can get this thing set up. We'll take a break, and in fact this picture is coming out to be too short and it is too small, and it's not quite readable. But what you are seeing.
A new block which we are getting is overall going to be larger than its previous one.
Yes.
That is being
Yes. So we are stopping now.